let me begin by defining principal stresses and principal planes. Principal stresses are the maximum and minimum normal stresses at a point. So when I talk of principal stresses, it means the normal stresses. And principal planes are the planes on which principal stresses act. We have learned in the previous module that if we know the stresses on two mutually perpendicular planes at any point A, that is on vertical plane and on horizontal plane, then we can find out what will be the normal stresses sigma nn and tau nt on different planes passing through point A by varying this angle theta. We found that the normal stress on any plane passing through point A can be written as sigma xx sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta plus tau xy sin 2 theta. Now, by varying this angle theta, we can find the normal stresses on various planes passing through point A. To find the maximum value of normal stress at point A, we have to differentiate this normal stress with respect to theta. So let us find on which planes we will have maximum value of normal stresses, that is principal planes, and what will be the values of principal stresses. The sigma nn can be written as sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 into cos 2 theta plus tau xy sin 2 theta. To find the maximum value of normal stress, differentiate normal stress with respect to theta. We will get, this is a constant term, so its differentiation will be 0. For second term, we get sigma xx minus sigma yy by 2 into differentiation of cos 2 theta is minus sin 2 theta into differentiation of 2 theta, which will be 2, plus differentiation of this term, which is tau xy into cos 2 theta into 2. For maximum or minimum value of normal stress, differentiation must be equal to 0. From this differentiation, we get tan 2 theta equal to tau xy divided by sigma xx minus sigma yy by 2. So these are the planes on which normal stresses are maximum. These planes are therefore called as principal plane. So let me designate these planes by theta p. To find the value of maximum and minimum normal stresses, we have to find the value of theta from this equation and put in the equation of sigma nn. The equation of sigma nn contains cos 2 theta and sin 2 theta. Therefore, we will find out sin 2 theta and cos 2 theta from this equation. The values can be found by this simple procedure. Draw a horizontal line and a vertical line. On vertical line, mark shear stress tau xy. O is the origin, and on horizontal axis we can show sigma xx minus sigma yy by 2. If we consider this as AB as perpendicular and BO as base, then this angle becomes 2 theta p, because tan 2 theta p will be tau xy upon this term, as we have got here. Tan 2 theta p is equal to tau xy upon this term. So from this we can get sin 2 theta p equal to perpendicular upon hypotenuse. So this is the perpendicular and hypotenuse can be AO. The value of AO can be found by following the Pythagoras theorem, AO square is equal to sigma xx minus sigma yy by 2 whole square plus tau xy square. So AO is equal to, let us call this value as equal to r. So sin to theta p becomes tau xy upon r, and cos to theta p becomes sigma xx minus sigma yy upon 2 by r. So we will put this value of sin to theta p and cos to theta p in the equation of sigma nn to get the maximum or minimum value of normal stresses at a point. So we get sigma nn equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2. This term contains cos to theta, so instead of cos to theta we will put this term, sigma xx minus sigma yy by 2r. Sigma xx minus sigma yy by 2r plus tau xy into sin to theta. Sin to theta can be written as tau xy by r. By r. So we get sigma nn equal to sigma xx plus sigma yy by 2 plus this two terms, this bracket term and this bracket term gets squared up. So we get sigma xx minus sigma yy by 2 entire square plus these two terms also get squared up. So tau xy square, and this r and r is common. So we divide the entire term by r. If we look at this term, sigma xx minus sigma y by 2 square plus tau xy square, we know that it is equal to r square because r is equal to this term. Therefore, we can write sigma nn equal to sigma xx plus sigma yy by 2 plus this numerator will be r square, denominator is r, so we get r. So putting the value of r, we get sigma xx minus sigma yy by 2 entire square plus tau xy square root over. So this is the maximum or minimum value of normal stress at point A. But now we are not sure whether this value of normal stress is maximum or minimum. We have differentiated this value of normal stress to find that on these planes the normal stresses will be maximum or minimum. If we look at this equation, tan to theta p equal to tau xy upon sigma xx minus sigma yy by 2, we will see that tau xy, sigma xx and sigma yy are constant terms. So this equation will be like tan to theta p equal to a constant. Let us say some 1.2 or 2.3, anything can come depending on values of tau xy, sigma xx and sigma yy. If we look at this equation, tan to theta p equal to constant, this equation has two roots, and the two roots can be found by following this simple procedure. If we look at this angle 2 theta p and we draw the lines in this manner, this angle will also be 2 theta p, as these two angles are vertically opposite angles. So if this is tau xy, this becomes minus tau xy, and if this is sigma xx minus sigma yy by 2, then this becomes minus times of sigma xx minus sigma yy by 2, and this OD becomes again this square plus this square. So again this will become R. Now if we look at this triangle, we can find another value of sin 2 theta p equal to perpendicular upon hypotenuse, which will be minus tau xy upon R, and cos 2 theta p equal to minus sigma xx minus sigma yy by 2, which is base upon hypotenuse, which is R. So now we will put this set of root in the equation of sigma nn. In this equation we will put the another root to find the another value of normal stress, which will be either maximum or minimum. So we, by putting sigma nn equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta. So in place of cos 2 theta we can put this value minus sigma xx minus sigma yy by 2r, and we will get minus sigma xx minus sigma yy by 2r plus tau xy into sin 2 theta. So instead of sin 2 theta we can put minus tau xy upon r. So we will get minus tau xy upon r. So we get normal stress sigma nn equal to sigma xx plus sigma yy by 2. We can see here one minus is there and here one minus is there, so taking minus common we will get sigma xx minus sigma yy by 2 entire square plus tau xy square whole divided by r. This r is again common in both the terms. If we look at this term is again r square. So in the numerator we have r square, in the denominator we have r. So r square by r we get r. So by putting the value of r we get the normal stress as sigma xx plus sigma yy upon 2 minus r, which is under root of sigma xx minus sigma yy by 2 whole square plus tau xy square. So this is the another value of normal stress, which will be either maximum or minimum, that we are getting at point A. Now if we compare the two values of normal stresses that we have got at point A, this was the previous one, we will see that it is sigma xx plus sigma yy by 2, it is plus under root of this entire term, and the other value is sigma xx plus sigma yy by 2 minus into this entire term. So obviously out of these two values of normal stress, this one is the maximum value of normal stress and this one will be the minimum value of normal stress. So now we have got the maximum and minimum values of normal stresses at a point. We will designate the maximum value of normal stress at a point by sigma 1 and the minimum value of normal stress at a point by sigma 2. So we get sigma 1 as this term and sigma 2 as this term. So I will write sigma 1 we are getting as sigma xx plus sigma yy by 2 and sigma 2 as, so this is the maximum value of normal stress and this is the minimum value of normal stress. We have learned that the maximum and minimum value of normal stress at a point are principal stresses. So this sigma 1 and sigma 2 are principal stresses at a point. Now we will find the principal planes are given by tan 2 theta p equal to tau xy upon sigma xx minus sigma yy by 2. This is the principal planes, and on these planes these normal stresses are acting. We have learned that this tan 2 theta p is equal to constant. So this equation tan 2 theta p equal to constant has two roots, and the two roots are principal plane 2 and principal plane 1. Tan 2 theta p equal to constant will have two roots that will have an angle of 180 degree between each other. So from here we get to theta p equal to theta p1 plus minus pi by 2. Therefore the angles between the principal plane 1 and principal plane 2 is 90 degree. That is, we can say that principal planes are perpendicular to each other. We have learned that at this point A, if the stresses on vertical plane sigma xx and tau xy and stresses on horizontal plane sigma yy and tau yx are given, then we can find the value of normal stresses at this point. The planes on which the maximum and minimum normal stresses act are called as principal planes, and principal planes are perpendicular to each other. Let us say at this point the principal plane is sigma 1 and the other principal plane will be this, which is perpendicular to this, so it will be sigma 2. So we have found normal stresses on these two planes. With these two planes will have maximum normal stresses at this point, which the maximum will be sigma 1 and the minimum will be sigma 2. Now I want to find what will be the shear stress on principal planes. That is, we want to find the value of shear stress on principal planes. If we designate this plane by 1 and this plane by 2, that is, we call this direction as 1 and this direction as 2, I can write the shear stress on this plane will be tau 1, that is stress acting on plane 1 in two direction, and the shear stress on this plane will be the shear stress acting on two plane, because its outward normal is in two direction, the shear stress acting on two plane in one direction. So I want to find out tau 1 2, that is shear stress on principal planes. We have learned that at a point shear stress on any plane is given by tau and t equal to minus sigma xx minus sigma yy by 2 into sine 2 theta plus tau xy cos 2 theta. So if we want to find the values of shear stress on principal planes, we have to put the angles that principal plane makes with the vertical plane. That is, we have to put theta p. We have learned that sine 2 theta p is equal to minus tau xy by r and cos 2 theta p equal to minus sigma xx minus sigma yy by 2r. We found the values of principal planes here. As you can see, you can put either set, either this set or this set. So we get the value of tau and t, that is tau 1 2, because we are putting principal plane angles on this equation. We will get tau 1 2 equal to minus sigma xx minus sigma yy by 2. Instead of sine 2 theta, I can put minus tau xy upon r plus tau xy. In place of cos 2 theta, I can put minus sigma xx minus sigma yy by 2r. If you can see, both these terms cancel out and we get 0. That is, the shear stress on principal planes is 0. That is, there is no shear stress on principal planes. That is, I can put tau 21 equal to 0 and tau 12 as equal to 0. So principal planes are the planes of pure normal stresses and no shear stresses are acting on principal planes. So let us summarize what we have learned up to now. The maximum and minimum values of normal stresses at a point are called principal stresses. The planes on which principal stresses act are called principal planes. At any point, principal planes are perpendicular to each other because the angle between theta p1 and theta p2 was found to be pi by 2. At any point, shear stresses are 0 on principal planes. That is, tau 12 is equal to 0. We have learned that invariant 1 was sigma xx plus sigma yy equal to sigma nn plus sigma tt. Now this n and t plane are perpendicular to each other, but we also know that the principal plane are also perpendicular to each other. So instead of sigma nn and sigma tt, we can put the principal stresses, that is sigma 1 and sigma 2, because 1 and 2 planes are also perpendicular to each other. So this is a very important equation, because if we know these three values, we can directly find the value of minimum principal stress. We also learned invariant 2 as sigma xx into sigma yy minus tau xy square equal to sigma nn into sigma tt minus tau nt square. Now instead of n and t, which are perpendicular to each other, we can put principal stresses, because principal stresses planes are perpendicular to each other. Therefore we get sigma xx sigma yy minus tau xy square equal to sigma 1 sigma 2 minus tau 12 square. But we already found that tau 12 is 0. So we get sigma xx sigma yy minus tau xy square equal to sigma 1 into sigma 2. Now let us find the value of maximum shear stress at a point. Up to now we have found the values of maximum normal stresses at a point by differentiating the value of normal stress with respect to theta. Now we want to find what will be the value of maximum shear stress at a point. For this we differentiate the value of tau and t given as minus sigma xx minus sigma yy by 2 into sine 2 theta plus tau xy cos 2 theta. By differentiating with respect to theta to find on which plane shear stress is acting maximum, we get minus sigma xx minus sigma yy by 2 cos 2 theta into 2 minus tau xy. Differentiation of cos 2 theta is minus sin 2 theta into 2. Put this 0 for maximum or minimum values of shear stresses at a point. We get tan 2 theta equal to minus sigma xx minus sigma yy by 2 into tau xy. So again, these are the planes on which we have maximum and minimum shear stresses at a point. So we call planes as 2 theta s. Since this all values are constant, so we again get tan 2 theta equal to constant. Therefore this equation will have two roots. One plane will be of maximum shear stress and the other plane will be of minimum shear stress, and both will have angle of pi between them. So we get theta S2 equal to theta S1 plus pi by 2. Therefore, again we can say that the planes on which maximum and minimum shear stresses will act are perpendicular to each other, as they have an angle of 90 degree between each other. To find the values of maximum and minimum shear stresses, we have to find sine 2 theta and cos 2 theta from this equation and put in this equation. For this, again we follow the same procedure. This is the origin. If we call this as minus sigma xx minus sigma yy by 2 and this as tau xy, we have tan 2 theta equal to minus sigma xx minus sigma yy upon tau xy. So this is perpendicular and this is base. So tan 2 theta s equal to perpendicular upon base. So here we can put, so this will be perpendicular and this will be base. Therefore this angle will be 2 theta s. So from here cos 2 theta s can be written as base upon hypotenuse. So this is base and hypotenuse is again this square plus this square, we will get as r. So we get tau xy upon r, and sine 2 theta s equal to perpendicular upon hypotenuse. Perpendicular is this, which is minus sigma xx minus sigma yy by 2 divided by hypotenuse, which is r. Again this has two sets of root, one this and another can be found by drawing the diagram in this manner. This becomes minus tau xy and this becomes sigma xx minus sigma yy by 2. This angle is 90, this is 90, these two angles are vertically opposite. Therefore the third angle will also be equal in these two triangles. So from this triangle we can find cos 2 theta s as equal to base upon hypotenuse. Base is this and hypotenuse is again r. This square plus this square over root. We get minus tau xy base upon hypotenuse, and sine 2 theta s equal to perpendicular, which is this, that is sigma xx minus sigma yy by 2 and hypotenuse, which is r. Now we have two sets of equation, one for maximum and another for minimum. To find the value of maximum and minimum shear stresses, we put these two sets of equation, first this and second this, in the equation of tau and t. So we will get tau and t equal to minus sigma xx minus sigma yy by 2 into sine 2 theta, and sine 2 theta is this. So we get minus sigma xx minus sigma yy by 2r plus tau xy cos 2 theta, and cos 2 theta is this. So we get tau xy square by r. Therefore we get tau and t equal to this minus and this minus becomes plus. We get sigma xx minus sigma yy by 2 whole square plus tau xy square whole divided by r. The above term, that is numerator, is r square and this is r, so we finally get r. Therefore tau and t becomes root over sigma xx minus sigma yy by 2 whole square plus tau xy square. So this shear stress can be either minimum or maximum. Now to find the other shear stress, we put another set of roots in the equation of tau and t. We get tau nt equal to minus sigma xx minus sigma yy by 2 into sin 2 theta, and sin 2 theta will be taken from here, which is sigma xx minus sigma yy by 2r, sigma xx minus sigma yy by 2r plus tau xy cos 2 theta, and cos 2 theta again can be taken from here, which is minus tau xy upon r. So we get minus tau xy by r. This minus and this minus can be taken common from the entire equation, and we get sigma xx minus sigma yy by 2 whole square plus tau xy square whole divided by r. This r is common in both the terms. The numerator is r square, denominator is r, therefore we get this as minus r. Therefore tau nt is equal to minus sigma xx minus sigma yy by 2 square plus tau xy square. Now we have got two values of shear stresses, one this with a minus sign and other this with a plus sign. Out of this, plus 1 is obviously the maximum and the one with negative is minimum. So we have got the maximum and minimum values of shear stresses at a point, and the planes on which the shear stresses are maximum are given by these equations, that is this equation. We can see the maximum, that is this equation, and the minimum, that is this value of shear stresses, are equal in magnitude. Now we want to find what is the value of normal stress on maximum shear stress planes. For this we put the value of maximum shear stress planes, that is this planes, in the equation of sigma nn. The equation of sigma nn is given by sigma nn equal to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 into cos 2 theta plus tau xy into sin 2 theta. So if we want to find what is the value of normal stress on tau max planes, that is maximum shear stress planes, we have to put the value of this plane theta from the planes of maximum shear stress, which we have found here, that is these planes. So putting sin 2 theta as this and cos 2 theta as this, we get sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 into tau xy upon r plus tau xy into minus sigma xx minus sigma yy by 2. So we can see that these two terms by r, these two terms get cancelled out. So the normal stress on tau max plane is given by sigma on tau max is equal to sigma xx plus sigma yy by 2. We have earlier found that the value of shear stress on principal planes is 0, but the value of normal stress on tau max plane is not 0, and it is equal to sigma xx plus sigma yy by 2. We have learned from invariant 1 that the sum of normal stresses on two perpendicular planes is constant, that is sigma xx plus sigma yy can be written as sigma 1 plus sigma 2 by 2 from invariant 1. So if we know the principal stresses at a point, that is sigma 1 and sigma 2, we can directly find the value of normal stress on the tau max plane. Now we have found that sigma 1 was given by sigma xx plus sigma yy by 2, and sigma 2, that is principal stress 2, was given by and tau max equal to. Now if we subtract sigma 1 from sigma 2, we get sigma 1 minus sigma 2 equal to, these two terms will cancel out and we will get 2 times sigma xx minus sigma yy by 2 whole square plus tau xy square. So if we divide the entire equation by 2, this will cancel out, and if we look at this term, then this term is equal to tau max. So we get that tau max is equal to sigma 1 minus sigma 2 by 2. So this is another formula for calculating the value of maximum shear stress at a point. If we know the principal stresses at a point sigma 1 and sigma 2, we can directly calculate the value of maximum shear stress at that point. So let us revise what we have learned in this topic. There are two planes at a point on which maximum shear stresses occur, and these two planes are perpendicular to each other. One is the plane on which tau max occur, and other is the plane on which minus times of tau max occurs. The value of normal stress on maximum shear stress plane is not 0, and the value of normal stress on the maximum shear stress plane is given by sigma xx plus sigma yy by 2. Now let us find the relation between principal planes and maximum shear stress planes. We have found that the principal planes are given by this equation, 2 theta p equal to tau xy upon sigma xx minus sigma yy by 2, and the maximum shear stress planes are given by tan 2 theta s equal to minus sigma xx minus sigma yy by 2 into tau xy. If we multiply both these, we get tan 2 theta p into tan 2 theta s equal to minus 1. These terms will cancel out, so we will get minus 1. Now if the product of the tan of two angles is minus 1, then these two angles are perpendicular to each other. That is, we can write 2 theta p equal to 2 theta s plus minus pi by 2. So we get theta p equal to theta s plus minus pi by 4. Therefore we can say that the principal plane, that is theta p, and the shear stress plane, that is theta s, make an angle of 45 degree with each other.